for the introduction. So I'm going to give a talk about the fast alignment of fragmentation trees. And as the fragmentation tree concept has been already introduced in the previous talk, I'm trying to make the introduction a little shorter, but giving you the basic details. So the compounds we're interested in are metabolites, that are the small molecules in cells, organs, and organisms. And metabolites cover a wide array of compound classes, and therefore they have a large structural diversity, as you can also see in the compounds that are shown on the slide. And although there are a lot of metabolites in all species, less than 1% are already described in the literature. So the identification of new metabolites is a very important field of research. And newly identified metabolites often serve as leads in drug design, in particular antibiotics. Now, mass spectrometry is one of the key technologies for the identification of small molecules, since it has high sensitivity compared to nuclear magnetic resonance, which means that we only need few samples to analyze a compound. Further, it has excellent compound specificity, especially when it's coupled to a separation method. Then we can also analyze complex mixtures. And it's also often coupled to a fragmentation method to yield information beyond the compound mass. So what we do is using a chromatography to separate the compounds. Then the compound is ionized and fragmented, and the fragments are, the fragment masses are recorded. So then we have a fragmentation spectrum, and that are the spectra we are dealing with. And the usual approach to analyze such a spectrum would be a library search. But here we face several problems. On the one hand, some fragmentation methods are very limited in their reproducibility, especially on different instruments. And on the other hand, spectral libraries are vastly incomplete. So what if you don't find a hit in the database? Then you could do a manual analysis. Means that you try to annotate the peaks in the spectrum with the corresponding fragments, the fragment structures, and to find the fragmentation steps that lead to this fragmentation pattern. But this manual analysis is very time-consuming and requires expert knowledge. And as we are in the age of high-throughput analysis, what if you have to analyze 10,000 metabolites at once? Now, that is why Böcker and Rasche automated this analysis, resulting in hypothetical fragmentation trees. So we have, try it this way. We have nodes with molecular formulas that are explanations for the peaks. And we have the edges that correspond to the losses that got lost in the fragment and explain the fragmentation steps that lead to the fragmentation pattern. This fragmentation tree concept has been introduced for TANM-MS data, but already been extended for GC-MS data and multiple MS data. But if you have such a fragmentation tree, you still don't gain that lot of information about the compound structure. But what we can do is comparing the fragmentation tree of an unknown compound to fragmentation trees of known compounds to get the structural information. So why can't we just compare the spectra of the compounds? You can see the reason here. We have two pretty similar compounds on the left, that is cysteine and methionine. But if you have a look at the spectra, you can see that they don't share a lot of peaks. But if we have a look at the fragmentation trees, you can see that we can recover the structural similarity in the fragmentation pattern. And so we can see that the compounds are actually pretty similar. Now, as for sequence comparison, there are several ways to compare trees. For example, looking for using the tree edit distance. And here we want to use tree alignment. And as for tree alignments are a generalization of sequence alignments. So we have matches and mismatches, as well as deletions either in the left tree or in the right tree. Now, tree alignments have been already used for RNA structure tree comparison. And RNA structure trees are in fact ordered And herefore there are polynomial time algorithms. But for fragmentation trees, there's no sensible way of ordering the subfragments of some fragment. And in this case, the problem is max SNP hard. But if we have a fixed maximum out degree in both trees, then there's a polynomial time dp to solve the problem. And by the way, for the tree edit distance, the problem remains hard even if we have fixed maximum out degree. And we introduce another operation to the tree alignment problem. If you have a look at the left tree, then you can see that one fragment is missing here. This can happen if the peak was hidden under noise, then you won't oh no, okay. Then you won't detect it in the spectrum. But in fact, these both fragmentation steps led to the fragment at the bottom, as these two fragmentation steps in the other tree led to the fragment in the bottom. So what we want to allow is joining this single edge to the both edges in the right tree. Okay, now the tree alignment concept with joining edges has been introduced by Rasche and colleagues and was explained somewhat informally in the previous talk, and now here I want to give a rather formal definition. Now SUV is the score of the optimal local alignment of the subtrees rooted in U and V, and to compute SUV we need SUV of the subsets A and B. That means the score of the optimal local alignment of subtrees rooted in U and V using at most the children A of U and B of V, as you can see in the figure. And then we use this recurrence to compute SUV of A and B. We initialize the tables for, if one of the sets is empty, then we initialize the tables with 0. And for the non-empty child sets, we use the maximum of the match case, the deletion case in either the one or the other tree, and the join case in either the one or the other tree. And of course, the 0 as we are computing local alignments. Now, the match case is pretty simple. Aligning the edge UA in the left tree to edge VB in the right tree gets the score of the aligned subtrees rooted in A in the left tree and B in the right tree, plus the score of aligning the siblings of A to the siblings of B, and of course, the score of matching edge UA to edge VB. If we want to delete edge UA in the left tree, then we have the score of aligning the children of A to some children of V, plus aligning the siblings of A to the remaining children of V, and of course, the score for the deletion of the edge. Now, the join case is far more difficult to explain. Here we even have to consider pre-join. And yeah, as it is very difficult to explain, I will skip it here. And if you want to know the details, then you can ask me later. And if we have a look at real-world instances, we found that we have many different edge labels in the trees, which different from sequence alignment. For tree alignment, or for our application, this leads to negative similarity scores. And further, we are computing local alignments. So we find many 0 values in the dynamic programming tables. So the idea is to sparsify the tables and storing only positive table entries. Thereby, we face the following problem. If we have a table entry for the sets A and B that is above 0, then we have also positive entries for all supersets of A and B. And therefore, we need to slightly modify the dynamic programming. For the classical DP, we defined the score SUV of A and B as the score of the optimal local alignment of subtrees rooted in U and V, using at most the children A of U and B of V. And now we only slightly modify it to using exactly the children A of U and B of V. And then we need a final trick. instead of pulling the scores from the previously calculated entries, we push scores from entries that have been finalized. Now, both of the dynamic programming algorithms have the same worst case running time complexity, where the exponential part of the running time, which you can see here, is only dependent on the maximum out degree in the trees. And for our application, this maximum out degree is pretty small. In fact, it's something, for most of the fragments, we don't have more than 3 subfragments. And the sparse dynamic programming algorithm is way faster than the classical one, as we find really many zero values in the tables for our application. In addition, we developed an interlinear program where we have to maximize the score of the alignment. Therefore, as usual, we need a lot of variables. I don't want to explain them in detail. And we have several constraints. The first constraint is to ensure that for each edge, we decide whether we use the edge in the alignment or not, and if we use it, then how, means either a deletion or a mismatch or a match. Then the second constraint is to ensure that the subgraphs of both trees are really proper trees. And the third alignment is to ensure that the obtained alignments are consistent. Consistent means if we have 2 edges, then the descendant of the edge in one tree cannot be aligned to a non-descendant in the edge of the other tree. Okay, of course we have evaluated our algorithms on 3 different data sets. The first 2 data sets, what am I doing? Okay, the first data set is from TandemMS data from the mass bank. Here we have 343 trees. The second data set is 93 trees from TandemMS data measured on an Orbitrap instrument. And we have one rather difficult data set. Here we use TandemMS data published by Hill and colleagues in 2008 to compute 102 fragmentation trees. And for these data sets, the trees have really high out degrees, as you can see in the figures on the right side. Now, the running times for the mass bank and the Orbitrap dataset, here the running times are in the range of microseconds for both dynamic programming algorithms for over 90% of the instances. So we only had to look at the total running times. And we can see the overall trend already for these 2 data sets, namely the dynamic programming algorithm is faster if we use the sparse dynamic programming, and both dynamic programming algorithms clearly outperform the interlinear program, which was pretty surprising to us. Now, for the Hill data set, we had a more closer look to the running times, as it's a harder data set. And here you can see the total running times for computing the 50%, 60%, 70%, and so on number of slowest instances. And for the ILP, we could just use the ILP without considering join operations, as the other one was too slow. And even for this one, we could only compute running times or solutions for 75% of the instances, as for the remaining instances, the ILP ran into the memory limit of 2 gigabytes. And for this 75% of the instances, the method needed over 11 hours. And the dynamic programming algorithms were able to compute all instances, and the classical DP needed 11 minutes for all instances, while the sparse DP only needed 1 minute for all instances. So we have an 11-fold speed up. Now, having a closer look at the running times, we found that the 1% slowest instances needed as much time as the 99% fastest instances for both dynamic programming algorithms. So there are still some instances that are pretty hard to compute for dynamic programming. Nevertheless, we could speed them up we had an 11-fold speedup. And now you could think that there are maybe some instances that are still faster to compute with the classical DP, but looking at the 200 slowest instances, we found that the sparse DP clearly dominates the classical DP for all instances. Okay, now you have seen that there are ways to compute fragmentation tree alignments pretty fast, and now I wanted to tell you what to do with fragmentation tree alignments. Sebastian was already giving you some ideas, like the classification of compounds by clustering. And now I want to present you FT-BLAST, which is a tool to search in a database for a compound that is actually not in there. And this is the big advantage to a normal spectral search. And the search is based on fragmentation tree alignment similarity. So we're looking for compounds with similar fragmentation trees, and they might have also structural similarity. And the cool thing is that we can use a decoy database to compute false discovery rates to differentiate between true and spurious hits. And we evaluated the method by an leave one out strategy. Means we removed the query compound from the database and searched for similar compounds in the remainder, and we reported hits up to a false discovery rate of 30%. And here I want to give you just a hint of the results, but as we can see a lot here, we zoom in a little, and you can see there are many hits that have the same compound, the same color as the query compound, means that it are hits from the same compound class, and they are actually pretty similar. And further, there are many stars. Stars means, small stars means similar, structurally similar compounds, and big star means the most similar compound that was in the database. And this most similar compound was for 30% of the instances at the top position and for 60% within the top 3 positions. So yeah, let me conclude. We have developed three algorithms for tree alignment, 2 dynamic programming algorithms and 1 integer linear program. And the sparse dynamic programming dominates the classical DP, and both DPs clearly outperform the ILP. But nevertheless, we want to use the integer linear program as a heuristic, solving only its LP relaxation and applying some integer rounding algorithm for those instances that are still pretty hard to solve for the dynamic programming algorithms. And as we now are able to compute fragmentation tree alignments pretty fast, we can use them in several fields of application. For example, the FT-BLAST search tool for searching for similar compounds in a database, and clustering for compound classification, reconstructing metabolite networks, analyze drug degradation products, and the search for novel drugs. Yeah, and now I want to thank especially the computationally mass spectrometry group at our institute, that is Kai, Florian, Sebastian, who was giving the previous talk, and Kerstin, who will present a poster. Further, Markus Schimani from the algorithm engineering group, and the Mass Bank Consortium, and Hill and colleagues for making their data publicly available, and Alice Svatos and Marco Kai for measuring the Orbitrap dataset, the IMPRS and the DFG for funding, and the ISCB for making this presentation possible by a travel fellowship. And of course, thank you for your attention.